Okay, trying again now. I see a signal. All right, let's try this again. Sorry, folks. Okay, that's just a bug in the streaming software I use. Unfortunately, the microphone said it was fine, but you guys said you couldn't hear it, so I just had to reconnect it. All right, all good. So I believe you can all hear me now. I've just reset it all. Yep, good. Okay, sorry about that. So this week, welcome to week 6. We're nearly halfway through the course. We've actually just about finished half of all the material, or perhaps more than half of all the material. So you're doing great. You're making huge progress. With this lecture today, we're going to finish off the unit J14, which we started before. It'll probably take about an hour to do that. Okay, but it should be fun. We're going to solve boggle. We're going to do a complete solution to a game in this first part of the lecture. After that, we're going to go do a revision lecture, and the revision lecture will be driven by you. So it's up to you to ask me good questions. You can ask me questions about any part of the course, okay? And I encourage you to use upvoting and whatever on the chat so I can see which questions people are most interested in. And I'll try and answer the ones that you want to hear most, okay? Obviously, I can try and answer questions about the mid-semester exam or about material that you want to cover for the mid-semester exam. All right, let's move on. Okay, admin. Another reminder about academic integrity. Unfortunately, a bunch of people did the wrong thing in assignment 1. They're about to get an invitation from me to come and have a little chat. That probably means a mark of 0 in the assignment and possibly an academic misconduct finding. There's quite a few people who did that. Don't do it. What else can I say? Don't do it, folks. Academic integrity. It's really important. It's going to be really important for the mid-semester exam. Now let me just quickly talk about the mid-semester exam. If you go to Piazza, you'll see I've put a post there for this week, and in that I have some information about the exam. The core information is all on the course website. It's very clear, I hope. I've said on the Piazza post that I've created a channel in Teams for the exam, and you can message people there during the exam if there are any issues. Okay, it's a half-hour exam starting at 6:30. Okay, and it's going to be fast. Again, you're going to have to move fast, but it's not about typing fast. It's about thinking fast. Okay, you have to think fast. All right. Also, if you have an EPA, there's a handful of students who have EPAs. You should have received a message from me on Piazza yesterday. If you did not receive a message from me on Piazza yesterday, it means that you have not, the university hasn't notified me of your EPA. So please yell, okay? So please send me a new message, or if you can't get in touch with you, catch me on Teams or something. But yell if you did not receive a message from me yesterday about an EPA. All right. About the exam, another really important point about the exam, please be strategic. The early questions are really not hard. They should not be hard. None of you should find the early questions hard. So you should be able to find, you move through questions 1 and 2. There's 4 questions, right? Each worth the same amount of marks. So questions 1 and 2, you should get knocked over pretty quickly. So move through them quickly. Do them as fast as you can. And then you'll find question 3 is appreciably more difficult, but everyone should be able to do question 3. Okay? Everyone should be able to do question 3. It's no more difficult than the early parts of assignment 1. Okay? But obviously in a format that you can do in an exam, right? So it's much more compressed, time compressed. But in terms of the understanding and level of difficulty. Okay? So everyone should be able to get question 3 out, but you might find it a stretch to get to the end of it. Question 4, I don't expect many people to get to the end of question 4. Okay, it's going to be hard. You have to work really fast if you want to get to the end of question 4. That's by design. Okay, so I expect in the class of 400, just a couple of people maybe to get all the way through and to get full marks. All right. So other really important point is that there are marks for for each question has 5 tests, and most questions have progressively have different subparts. In questions 3 and 4, which are the harder questions, the first parts are probably not so. You make sure you get the marks for the first part, even if you can't get the marks for the second part, right? So if you're getting really stuck on the second part, skip on to the next question or something like that. Okay, be strategic. So don't let yourself get blocked on something you can't do, and just get the marks where you can. All right. So cloning. Yeah. So the way the way the exam works in terms of the technology, it'll be just like the lab exam. That is to say that there's a URL. I actually already posted the URL in Piazza. You won't be able to access it. The server is blocked. And it gets unblocked at 6:30. Once it gets unblocked, at that point you can then clone the repo. Everyone gets a different exam. Yay! So I made 400 exams on the weekend. Everyone gets a different exam. You'll get your exam when you clone it. Okay, so you have to clone it into GitLab into IntelliJ. All right, you don't fork it; it's already forked for you. You just clone it, and then it's just like the stuff you've seen before. You'll have four Java programs in your repo. Each one will be one of the questions. It'll be Q1 something, Q2 something, Q3 something, Q4 something. You go in there, and then inside there, there'll be fix me's. You go to those fix me's, fill them in. There will be tests in the drop-down menu. Make sure the tests work before you press push. Once you're all good to go, commit it and push it. Make sure you don't commit and push stuff with syntax errors. If you do that, it won't compile on the CI, okay? So you make sure that it's working, passing the test before you commit and push. Whatever you do, make sure you push before the exam ends, okay? You only get marked on what gets pushed when the exam ends. And the way that the technology works is when the exam ends, bang, basically a firewall comes on and you cannot connect to the server. You will not be able to push after that point in time. It's simply technically impossible, okay? So you have to push by the deadline. It's possible the CI will not have finished by the time you want to finish, and we don't know what's going to happen to the CI. This is the first time anyone has ever run such a huge 400 people at once doing the CI. In past semesters, we've had them staggered exams, different times, so we've never had 400 at once. The tech people have worked really hard to try and make it work, but I don't know. We're kind of crossing our fingers, hoping it's going to work here. It doesn't really matter. I mean, it's kind of nice feedback for you, but it doesn't actually matter. What really matters is what you push, okay? So just make sure you've committed and pushed the stuff by the end of the exam. That's the most crucial thing, all right? Anything else? Yeah, I did have a busy weekend. Katrina, I had a very busy weekend. I'm pretty tired. COVID's no fun for lecturers, just as it is no fun for students. It's not fun for any of us. I know that. The mini camera. Oh man, I forgot the mini camera. Oof. Someone asked for the camera. Sorry, there we are. It's on. Okay. I thought it was on. Sorry. What else have I got? The last thing. Oh, guest lecture. We've got a great guest lecture on Friday. Let me quickly go to the web page here. Oh, one more thing I want to show you. Some of you aren't yet totally familiar with the way all this stuff works. Please remember, every week this thing here tells you what's going on during the week. Also, notice the lectures are all here. You don't need to go to Echo to see your lectures, okay? They're all here. So if you want to go to the Java lectures and revise them, they're all here, okay? With little links. That's all your lectures, okay? And if you go to the guest lectures, it tells you what's coming up, and you come to Friday's guest lecture, you go here and click on that little link there, and you can find out all about our guest lecturer. And our guest lecturer is Amanda Barnard, Professor Barnard. She's an amazing researcher, one of the most outstanding researchers in Australia. I mean, literally one of the most outstanding researchers in Australia. And she does crossover work between nanomaterials and high-performance computing, machine learning. Okay, so she's a very, very interesting person. You know, she's got read all this stuff here. She's got an amazing CV. And she's putting aside an hour of her time to talk to you. So please come along on Friday, and don't forget these are examinable in case you needed the stick to come along, but you should just come along anyway because it's going to be a great speaker. There's no reading time, folks. It makes no sense in a. Sorry, I'm just going to the. I'll finish this, then I'll go to the questions. Okay, so please come along, see Amanda. She's going to be a great lecturer, and you are very privileged to be at ANU, where you get access to people like this who come and talk to you in your class, and better still, answer your questions. So we're going to do it like we did for the 1140 guest lecture. I want you to put your questions here. I will have a Zoom chat with Amanda. She's going to be on campus. And or somewhere else anyway, and then I will ask her the questions as they come up on the chat. All right. So make sure you think ahead about, have a read of her webpage, have a read of who she is, and think about questions, good questions to ask her. Ask her about anything. Ask her about her career, where she went to school, anything you like. I mean, that's what the nature of this is. You get to know someone really, really impressive, really famous, and ask them questions about how they got there, what made them excited about what they're doing, that sort of stuff. All right. Now back to questions on the chat. Someone asked if there'd be reading time. Reading time doesn't make any sense in an open book exam, okay? So as soon as you clone that exam, it's yours, right? I can't stop you from writing, obviously, right? So there's no notion of reading time for an open book exam. It doesn't. The concept doesn't apply. You just get 30 minutes, okay? You have a 30-minute exam, and you just have to work as fast as you can to get through that exam. Don't stress if you don't get to the end of it, okay? I'm not expecting you to get to the end of it. It's by design, all right? If you've ever studied maths, it's pretty normal to have an exam where you don't get to the end of it, okay? That's quite okay. Don't stress about it. The exam is redeemable, so if you totally tank, you shouldn't. But if you did, don't stress, it's redeemable, okay? And it's only worth 5 marks, all right? So all those reasons, don't stress. What this is really here for is to help you get a sense of whether you're up to speed with the course. And if you're getting above 60 in the exam, you're up to speed, okay? If you get less than that, so it's 60 minutes from the time I tell you, okay? 60 minutes from 6:30, well, whenever I hit the button to say go. Because what happens, someone's asking how long the exam goes for. The way it works is that basically there's just a piece of technology which opens the gate to the whole web server and then shuts it, okay? So I'm going to open that at 6:30. Everyone can grab it, and then at 30 minutes later, bang, the gate comes down. You won't be able to push or anything, okay? It's just like that. It's very, very simple. It's not done by person or anything like that. There's no timestamps, nothing. It's literally the network access to that server gets opened and shut, right? So it's very, very simple and crude. So you can't submit the exam late. You simply can't do it. It won't be able to push. Any other questions about the exam, about logistics for tonight? Open book. Yeah, very important that you know this. Good question, Alexander. Yeah, it is open book. I can't stop you from doing it. It's an open book exam. The one thing that you mustn't do is don't violate academic integrity by misrepresenting someone else's work as your own. Okay? You can do a web search. Okay? No, someone's asking about what an EPA is. EPA, if you don't know what an EPA is, you don't have one, so don't worry. An EPA is for certain people have certain conditions or whatever it is that mean that they need special consideration when they're doing certain things on campus. You know, so you might have some medical condition or something like that means that you can't sit still for 30 minutes because you're on crutches or whatever it might be, or you've got your leg that needs to go on a chair or whatever it might be. There's a whole lot of different circumstances. But if you had one of those, you would have gone through the university and it's an official thing and there's an official document that says this person has this, needs this consideration, blah, blah, blah. So if you don't have an EPA, if you don't know what an EPA is, it pretty much means you don't know. If it passes with warnings, the tests are going to give you a green tick or a red cross, just like all the other tests, okay? There's no notion of warnings here. Yeah, I mean, IntelliJ does all those fancy checks. When you commit, ignore that stuff, okay? All that matters is the tests that I give you. I give you tests. I give you unit tests. You either pass or you fail the unit test, okay? You want to get 5 out of 5 on each question, okay? If you don't get 5 out of 5, that's okay, right? You'll get 4 marks if you get 4 tests. There are no true or false questions. That's correct. I said that on the webpage. There are no true or false questions. There's just 4 programming questions. Go read the webpage. It tells you all about it there. So I won't answer any more of those questions. But go back to Alexander's question about open book. Yeah, absolutely. It's open book. Okay. So the deal is you need to do this exam yourself. Actually, yeah, hopefully that's not a surprise to anyone. You need to do it yourself. You need to do it on your own. Okay. But beyond that, you can use the course notes. You can use the lecture notes. You can go to Google or whatever to ask for syntax on how to do something if you want, right? That's allowed in this exam, okay? Unlike the lab exam, okay? This exam, it's open book, which means that you can do all this stuff, all right? Yeah, that's right, Benjamin. There's only 4 coding questions. That's exactly right, but it's all on the webpage. Go check the webpage. It tells you this very clearly, all right? Any last questions on the exam? I'm going to move on to the lecture now, unless there's any more questions on the exam. All right, if you have any more questions, wait until the revision part of the lecture and I'll answer them then, okay? So try and hold off on your questions about the exam for now, and we'll move on to collections. Remember, we're studying collections. Collections are like bags, and there are a couple of fundamental collection types. Can anyone name them? It's not going to be in the exam because the examiner goes a week 4, but just for the sake of this lecture, can anyone name what the key types of collections that Java has that we're studying in this course? There are 4. Right? There are sets, there are lists, there are maps, and there are queues. Okay? And we're going to study sets, lists, and maps. Yep, great. Okay? Yeah, perfect. Okay? And in this course, we're going to focus on maps, sets, and lists. Okay, those three there. And we're going to implement in this course later on, we're going to implement from scratch those 2 different ways. Each one, we're going to implement 2 different ways, all right? So that's what we're going to do. And what we're doing today is we're diving into a solution to a game, and we're going to use collections in the game. We're going to use sets in the game. What's the property of a set? The property of a set is that it has no ordering and no duplicates. Okay, no ordering and no duplicates in a set. That's the mathematical definition of a set. It's also the way Java does a set. Okay, a list, on the other hand, is ordered by definition and may have duplicates. Okay, so if you have a bowl of fruit that is a list, then you could have apple, banana, banana, apple, orange, and that means you've got 2 apples and 2 bananas and 1 orange, right? But if it were a set, the set would include, if you just put those things into a set, there's no concept of duplicates and there's no concept of ordering. So you just say there exists orange, there exists apple, there exists banana, and there's no sense of how many there are. They exist or they don't exist. That's what a set is, okay? That's the difference between a set and a list. And a map is where you have keys and values. So you can look up using a key and retrieve a value. And we did that example in the first part of J14 where we had a class and we had we looked up UIDs, and the UIDs were attached to the student and all the information about the student, and you could search there and you could do sorting as well. All right, with that, we're going to dive back into the code and pick up where we left off. And what we did in the last lecture, for those of you who remember, is we wrote two simple tests. Okay, the first thing we did, well, we imported this little piece of code here from the previous, some code we wrote previously. We imported this from code we wrote previously. All this thing here is producing a randomized boggle. Let me quickly go to the web page to remind anyone who's forgotten what boggle is, remind you what it is. This is actually really important. If you don't understand this, you're not going to follow the lecture. Okay, it's a game. It's a game where you have a plastic cover over this thing and you give it a big shake, and these dice all fall into place in a randomized way like this. It's just some random ordering. And then you have to make a path that makes a word by starting at any letter you like. So N-E-T, and the rules are the letters have the dice have to be adjacent or diagonally adjacent. Okay, so you can say N-E-T, G-E-T, that's net and get, and set, S-E-T. Okay, so what you have to do is find as many words you can, and you get more marks for longer words. All right, and what we're going to do is we're going to write a program that finds all of them, every single word for a given randomized game. Okay, that's what we're trying to do. Now, what we wrote in last week's lecture, the one piece of code we did write, is a little helper called neighbors. And what that was doing is we give each one of these spots a number, so it's 0, 1, 2, 3, 4, and so forth. We give each position a number up to 15, so there's 16 spots, and that's 0, and that's 15 down there. And then what we do is you say for any one of these, who are our neighbors? And because you can go diagonally in this game, it means that if you're in one of these positions, like P, it's got 1, 2, 3, 4, 5, 5, 6, 7, 8. It's got 8 neighbors. Okay, so P has 8 neighbors. R, it's got these ones here, that one there, that one there, that one there, that one there. They're then the neighbors of P. Okay, so all the dice that surround it are the neighbors of P. R, on the other hand, only has 3 neighbors, right? It's just got those ones, okay, because the rest of them are off the board. All right, and H has got 5 neighbors, right? So it's got these ones. Okay, so we wrote ourselves a function that tells us who the neighbors are. So I give it a position and it says, okay, here's my neighbors. And what it does is it produces that as a set. Okay, here's the set of my neighbors. So we have a list of 16 positions, and for each position we get a set saying, oh, here's the neighbors for this position, here's the neighbors for this position. And what that means is that when we go and try and solve the game, every time we land in a position we can say, oh, for all of our neighbors do the following, and then we can iterate through all our neighbors. Okay, so that's what that is. And we wrote that, here it is up here. We created this thing here called neighbors, and here we constructed it all, and down here we wrote some tests. Okay. Oh, and something very important. Someone pointed out at the end. Can anyone notice something very interesting? Someone pointed out at the end of last lecture. I think this here. I think it was that one there. I did a typo here and had that as N. Right. I think that's what I did. Right. And now, what's really interesting is I made that mistake, and 2 of you pointed out the mistake, and I fixed it. Ncol has the same value as Icol. Oh. This has 2 mistakes here. No, it's not the same value. See that I changed this to I, right? So Isaac, so I made that mistake in the last lecture, but I fixed it. And if you go back in the video a moment ago, you'll see it's already fixed. Yeah, that's right. Okay, exactly. Last lecture I made that mistake, right? So why is it significant? What's so significant about the mistake I make, except the fact that I made a mistake, but you've seen me make lots of mistakes? Why is this interesting? There's something you should have noticed that's really important. Isn't that a quote from you? Yeah, that's right. You said that last time, right? That's right. So someone pointed this out last lecture. I fixed it at the end of last lecture, right after the end of the lecture. That's right. Nathan points out it passed the test. This is actually a crucial observation. Absolutely crucial that you notice that, okay? The observation is that this passed the tests. The n is less than or equal to 15. Yeah, wow. 2 mistakes here. Okay, so we've got 2 mistakes here. Thank you. Someone else noticed another mistake. Okay, what's really important here is that we wrote this code, we wrote some tests, and we made 2 mistakes, I believe. If this latest one's correct, we made 2 mistakes, and yet the test passed. That's a really important lesson to you, because what that's telling you is that tests can often tell you where you're wrong, but they can easily miss cases. Okay, it's extremely hard to write good tests that cover all the cases. It's actually extremely hard. Okay, now these ones here we didn't put a lot of thought into. We just wrote them during the lecture, and we could have certainly done a better job than that. But it's very important for you to notice that we wrote these tests, then we wrote the code, and yet our code passed, yet it had bugs in it. Okay, that's what I wanted you to really notice. I believe that they're fixed now. If they're not, someone should yell. So let's just quickly walk through this. We're going to go through all the distances. There's all the distances. So these are the distances from a given die, and you see that there are 8 possible positions that surround a given die, and they're all the distances. And then what we do is for each distance, we find the position that is at that distance. That's n, and then we find that's a neighbor, right? And we find the column of the position, and we see if that column is off the edge, right? If it's off the edge, then we've got a problem, right? And if n is greater than, and we also excluded if n is above or below. If it's below 0, then it's obviously off the edge, and if it's above 15, it's off the edge. Okay, so and we just check that these columns. Okay, so that's how we did it. Now let's get on with and write the code. Okay, I think I've explained that plenty enough. Right, so what we're going to do now is we've wrote this thing here that's going to solve the boggle. Okay, so here it is. Here's our boggle solver, and what's in there? Nothing. Okay, this is how we write our tests, but let's just run those tests again, test neighbors. That's going to pass, even though we had bugs in it and we fixed those bugs, it's going to still pass. And then the other test was, what's the other test? Test boggle. This one here, we'll run this test boggle. And it fails, of course, as we expect, because we haven't written anything yet. Okay, so now let's get on and write this. And the first thing we're going to do is we're going to write ourselves a function that reads in a dictionary. Okay, because the game says you have to find these words. You can't just make up random strings. They've actually got to be real words. Okay, and the way we're going to do it is we're going to read in from a dictionary of real words that I happen to have in the repo here. And we're just going to read in those, and we're going to check all our words against that dictionary. Okay, so so let's write ourselves a piece of code that does that, and we'll call it read words or something like that. Okay, so static void void read words, and then we'll take file name as an argument, string file name, and we're going to take a set of words. Okay, the words form a set, right? There's no notion of duplicates in a dictionary, or at least there shouldn't be. And so we're going to take in a set of words. So set string words. Okay, and that'll be empty to start with, and we're going to put words into it. Okay, like that. And then what we're going to do here is we're going to go and read these things. Okay, so and we'll give ourselves a little counter. Word count equals 0. Like that, and then we'll do a try. We have to, because we're going to read in from a file. We're going to do a try and catch thing here. So we get scanner s equals new scanner. We're going to read in from a file. New file name, like that. And yep, there we are. And we're going to add that. What's the matter with scanner here? Add catch, yep. There we are. Okay, so we add the catch. That's just the exception handling, which Java requires us to do. Okay, so now, and by the way, we're going to cover exceptions in more detail later in the semester. So at the moment, this is just more Java boilerplate, which you just have to put up with, and later on it'll become more clear. So what we've got ourselves now is we've got a scanner which is going to read stuff in from the file. Okay, and what we're going to do is going to say while s.hasNext, as long as there's more words to come, let's read it in. And then we'll just say string. We can just do string. What we want to do also is we don't know what the case of the letters are, and what makes sense is just like here, turn everything to uppercase, just so we don't have any ambiguity about upper and lower case. We're just going to turn everything into uppercase. String word equals s.next dot to upper, right? So that's how you convert something to uppercase in Java. And then we'll words.add. We're going to add it to our set. Add, oops, I can just type, add word, and the words we've read in. Oops, what's happened to my mouse? There it is. Okay, so then we'll just add it, also increment our word count. All right, now our word count should be the same as the size of the word set at the end, right? It'd be interesting to see if it wasn't. If it wasn't the same, that would mean there would be a duplicate. Okay. And now what we can do at the end is we can just print out what we read. I think we're done here. We can say s out, read in, okay, so now we're going to see the size of the set. Word count is kind of redundant in there, but it might not be later. Okay, so to start with, so someone asks, isn't word count redundant? It is kind of redundant, but we're going to use this later. Okay, at the moment, this should agree with this. They should be the same, right? We hope, unless a dictionary's got duplicates in it, they should be the same. I don't know if the dictionary does or not. I actually haven't looked. So let's just see this, and then what we're going to do here is we're going to create ourselves this new word set, and then pass it to that function to read it in, and then we'll have a set of words. Okay, so set. Notice I'm going to declare the set. Oops. Set of word string. Well, not word. String. Like that. Set of string words equals new. Now, what I want to show you here is that this here where I've declared words, that there is an interface type. It's a container type of set, okay? But we've got to make it concrete on the right-hand side because you can't make a new interface. You have to make a new concrete type. So we're going to say new hash set. Well, it doesn't really matter which one we use, but we'll just call it a hash set now, okay? So there it is. Just create an empty set. And then what we'll do is we'll say read words. And then what we have to pass the, I think I'll put it here, resources / words / dictionary. .txt. All right, and then we'll pass it words. Okay, hopefully that will work. And let's just check to see if I actually did put it in here. There it is. Okay, words. I did check that earlier. Okay, so there's our. You see up here, resources words dictionary.text, resources words dictionary.text, and then we still don't have it. We haven't solved that anything yet, so we're still going to return an empty list. Okay, but now we've got a main method somewhere. Yeah, there we are. And now what we can do is we can say a set of words, strings, sorry, set of string, what is it, solve boggle? Yeah, it's a list, not a set. Okay, list of strings equals solve. Why am I not getting this working? Oh, I didn't declare this as static. Everything else is static, so it needs to be static. It's interesting. I'm not sure why I made that a list. So boggle, there we are, and we've got to give it the boggle we gave, which is called boggle. Okay, so that boggle was the 16 dice. Okay, now let's run this main method. What does a dictionary file look like? It's just literally a dictionary of words that came out of off a Unix dictionary, right? When you get an operating system that has a standard dictionary, it's just a standard dictionary, nothing special. Okay, they're supposedly all real words. I don't know that AA is a real word, but supposedly it is. Okay, so this is a standard dictionary that I just got off of a standard Unix system, and supposedly it's only got real English words in it, although I've never heard of AA as a word. All right, so there it is, and we've read in, so it's got 80,000 words in there, and you see the set size is the same. So it is redundant, going back to the previous question. So we've read the words in. What do we want to do next? Okay, so, well, what we want to do now is we've got a set of words, and what we want to do is we want to basically, now we're going to need to think of the algorithm, okay? And really what we want to do is we want a simple way to do this is, a simple way to approach this problem is to start at each die, like that, and then search for all the words that you can find from that one die, okay? You got to search from there, and then we'll do it from that one, then we'll do it from that one, then we'll do it from that one. And when we've done that, we'll have exhaustively found every possible word that you can make out of this. So let's write the code for doing that, okay? So, so what we're going to do here is we're going to say, we've read the words in. Now what we're going to do is say for int I equals 0, I is less than dice.length, 16, I plus plus, and then we're going to find all the words at that dice. Okay, find words, and then we will say words. And one thing we want to do is, there are many ways to solve this, by the way. So someone's asking, can we use a non-binary search tree? There are so many different ways of solving this problem. I'm going to show you one of the simplest, okay? So you can think about other ways of solving it later. One thing we're going to do here is we're going to create ourselves a little array of booleans that can get used for knowing whether or not we've used one up. Because one of the important rules of Boggle is that you can't use a particular die twice for a certain word. Okay, so I can't do, the word goon isn't possible. Goon is G-O-O-N. I can't do G-O-O-N. That's not legal in Boggle. You have to do G-O-N. That's all you can do, okay? So you can't use a single letter twice, okay? A particular die twice. If the letter is there twice, like that N and that N, that's okay. But you can't use the single die 2 times over, all right? So we need to keep tabs on which ones were used. Okay, so we're going to create ourselves an array of booleans for doing exactly that. So boolean, whoops, IntelliJ did not help me there. Boolean used equals new boolean dice.length. Okay, so we've got ourselves an array of booleans, and we can use that to say, oh, we've used it or we haven't used it. And we have to for each time we do a new word, we have to say yes, we've used it, and then we have to clear it again when we're finished doing that. Okay, so we're going to use that little array a lot in this code. Okay, so that's the little array of booleans of things that we've used. We're going to pass our boggle in and our starting position, which is I. Okay, and the other thing that we're going to do is we're going to make this method recursive, okay? This is going to be the interesting part. And so what it's going to do is, let's go back to here, the picture. What we're going to do is we're going to recursively say, okay, all the words that we can get from here equal the words that start with H that are followed by everything that comes from here, right? So if we can find all the things that come from here and put H in front of it, then we've found all the things that can start with H. Okay, so what we do is for each of H's neighbors, we say the words that we can get from H are equal to all the words we can get from H's neighbor, without using H again, all the words that we can get from H's neighbor, and appended to H. Okay, so what we're going to do is we're going to do this thing recursively, and so what we have here is the starting string, and the starting string will be nothing. Okay, and gradually you build this string up as we go to each point. Okay, this hopefully will become clearer soon if that explanation wasn't crystal clear to you yet. And what we're going to do here is we're going to create another thing here, which is our Boggle words set of strings Okay, so that's all the words we found. Oops. I didn't mean to do that. Come on. There we go. So I've just created another set. That's the ones that we found. These are the good words. That's our solution. Okay, so we'll pass this to our we'll pass that in here too. Boggle words. Okay, so that's a set of all our solutions, and we'll return boggle words here. We'll make an array list out of the boggle words because it wants a list. Okay, so boggle words. Oh, I know why I wanted a list. You know why I wanted a list instead of a set? It's kind of natural to find these as a set, but later on we're going to sort them. Okay, it's kind of nice to sort them. So we're going to sort them, and to sort things, you need a list. You can't sort a set. You can sort a list. Okay, so we're going to turn our set of boggle words into a list and return that. All right, and at the moment this won't work because we haven't written find words. So let's go and write find words now. So so find words, remember, find words is going to add words to the solutions here, which is the boggle words, which initially is nothing, it's empty. And it's going to only add words that are actually part of the word set. And it's going to take note of which dice we've already used, okay? And we're going to search for things according to this particular boggle, that is that particular arrangement of the die, and that is our starting position. Okay, so that's one of these starting positions, 0 through 15. Okay, and that's a starting string which will grow as we make our path longer and longer. That'll grow. Okay, so now let's go say static void find words, and we'll take in our set of strings. That's the boggle words, that's the solution, and we're going to add stuff to that, boggle words. And we're going to take a set of dictionary words, set of string of actual real words. That's the stuff we read in from the dictionary. And then we're going to take in, what is it, use the Boolean array of which dice have already been used up, because we can't use a dice twice. Used. And we're going to take in the char array of the actual characters in the that 4x4 array. So that's our boggle game. And then integer, which is the position, the start. That's where we're starting off. We're going to start a path from that particular position. And then we're going to call this thing a prefix because we're going to build a string with this at the start of it. So we'll say string prefix. Right, and notice that we start off with a prefix of nothing, which is what we have here. Okay, so this thing here will find all the words at a given point and add them to this prefix. Okay, so it'll only and it'll add if they turn out to be a real word. That is, whatever's found at this point with this at the beginning of it is a real word. Then it'll add them to boggle words. Okay. And then we do this for each of the 16 positions. Okay, so let's start off. Now, what we need to do is we need to mark out the fact that the die that we're at is used, so that as we continue searching, we don't use it again. Okay, so we'll say used start equals true. Okay, and we're going to, at the end of this whole thing, we're going to say it's false. Okay, so in anything we do in between times needs to be aware that that we've used up this particular die. Okay, this particular die is used up any time in here. It's used up. So here we say we've used it, so that means we don't use it again. And down there it says, okay, we're done with it. Which means if we go and search from a different place, that's okay. All right. So now what we're going to do is we're going to say we're going to take the particular. We're going to create a candidate word and see if that candidate word is valid. Okay. So let's start off. Now, the most basic thing we can do is we can say the candidate is equal to the prefix plus whatever die we're at the moment, which is boggle. Okay. Now, if that's a real word, which it could be, then we can add it to the list. If it isn't, then we'll go to to our neighbors and see if they can add something on and create a real word. Okay. So what we'll do is we'll say if now. The only words we can put in here are words that are 3 or longer, right? So we'll say if candidate.length is greater than or equal to 3, and it's in our dictionary of words, and word. So how do we know if it's in the set? We use the contains. Contains is the way we find out. Contains, if our set of words contains this particular candidate, That means we found a real word. Yay, okay? Okay, so if that's true, then we add it, okay? Hooray, we found it. Okay, we can still keep searching though, regardless of whether or not what we got was a valid word, because you may be able to put valid suffixes on the word and it's still boggleable, right? So you can put ing on the end of the word and it's still in the subsequent words valid too. So we don't stop yet, right? We keep looking, okay? So then we'll say, then what we'll do is go to all of our neighbors and say, hey, can we add, can you grow this, okay? All right, so for int and in neighbors, remember we created the set of all the neighbors of get start, that's us, okay? So for all of the positions that are our neighbors, we can go and investigate them if they're not already used, all right? So we'll say if we haven't already gone to them, oops, if we haven't already gone there, then recurs, okay? So find words with this prefix, okay? So we'll say find words, boggle words, oops, boggle words, words used, boggle, and we're going to start at n, our neighbor, and then the prefix is going to be where we are at the moment, which is our candidate. Okay, so like that. And that might be it, right? I don't know. Does that look good? Have I missed something? Let's have a look at that. And then, all right, that's our solution. And then let's write something out. Okay, so well, I don't know if this is going to work, right? This is actually pretty hard to get right, so we may not have made it work. Let's see what we should print out. Okay, we should print something out. So S found solution.size. Found that many words. All right. And then what we can do is we can go and list them all, right? And just go and list them. And then we can say for W in words, a solution. All right, someone found a bug. All right. All right, now let's see if this actually works. The moment of truth. I've probably made a mistake. Oh, yes, I did. Let's see, what have I done here? What have I done? All right. Okay, index 0 out of bounds for length 0. Okay, where is this? Let's have a look. Check index array list.get, find words. Okay, neighbors. Neighbors hasn't been initialized. Why is that? Neighbors. Why is that list of neighbors not? They should have all been initialized. Let's just check this. Okay, index 0 out of bounds for length 0 means there are no neighbors. Why are there no neighbors? Okay, this code, just so you know, when you do this, the code, that means this should have been initialized before we before the program runs. Okay. So let's just I'm confused by that. So let's just do some debugging right here and now. We're off script again, of course. See what happens here. N. Okay, and that should be 16. And if it isn't, we've got a problem, and I don't really understand what that problem is. So let's have a look here. N is 0. Why is the neighbor 0? I'm just so confused here. Okay, we can solve this instead of using. Oh, I know. I forgot to write the word static in front of this. My goodness. Okay, you have to write the word static. I just made a basic mistake, folks. I'm kind of blushing. I'm so embarrassed I made such a simple mistake. If you want a piece of code to run when your class is loaded, you have to put the word static in front of it. Okay, and I may have had that there. I may have just deleted or edited out at some point, because we did test this before and it was working fine. So I'm not sure what I did. I must have somehow at some point I must have messed that up. Let's run it again now. Yay! All right. Wow, cool. It did something. There's a bunch of words. Look, it's got words like saintly and is that? Wow. All right, teensy. Is this for real? Okay, let's have a look. Found 170 words. Read in that and found 170 words. Wow. So melt. Let's have a look there. Is melt a real word here? Melt. M-E-L-T. Yeah. Okay. So we've got something here. Now let's run our test and see if our test passed. Run test boggle. Okay. So what this is doing? Aha! It did not contain ire. Our solution did not contain ire. That's interesting. Should it have? So this is the boggle. Hey, should it contain ire? I don't think it does. I don't think there's any ire there. So that was one of the examples that came up in the lecture. I don't even see any ire. That's a mistake. Okay. All right. So a mistake in the test. That doesn't make sense. False. Okay, we should get rid of this, by the way. These are ones that it did. Oops. Okay, all right. So we run now. And we passed the test. Fantastic. Okay. So, folks, I believe we have boggle working. Okay. Let's just do a couple of things. First of all, we'll do one more thing with collections. You should be all clapping now at this point. We've actually solved a game in the lecture. Now what we're going to do is do two things. We're first of all going to print it out in a slightly more easy to understand way. Then we're going to do two interesting optimizations. I want you to think, while I'm doing this part, I want you to think, how can we have made this faster? Okay? Because there's two things we could do which will make this appreciably faster. And we're going to do that in a moment. All right? So I want you to think, how could we have made this appreciably faster? So what we're going to do here is we're going to say, first of all, we're going to sort this collection. Okay, so we'll just sort this collection. And what would be nice, right? What would be nice is if we could sort the words we got by length first and then alphabetically. All right? Length first, then alphabetically. Why do we want to do that? Because in boggle, you get more points for longer words, and alphabetical makes sense because it's easier to read. So let's just do that, okay? So the way we do that is we can call the sort method on collections. Collections dot sort solution. There's a solution. And then what we're going to do is write ourselves a lambda, which does the sorting. So the lambda is going to take two strings, string, oops, S1, comma, string, S2, right? And then we're going to write ourselves this lambda, which is going to compare those two strings, okay? And the lambda is going to say, if they're the same length, then we sort them alphabetically. Otherwise, we put the shorter first, the longer first, I guess. So we'll say s.length, if they're the same length, s1.length equals s2.length. Then we just return the regular string comparison. Return s1.compare to s2, like that. Otherwise, we will return the difference in the length. Return s2 dot length minus s1 dot length. Okay, so hopefully that will do the trick. So what that's done, and let's just run through this again. Solve boggle produced a set of boggle words. We converted the set into a list. Okay, and then we took the list and we sorted it using this lambda here, which takes two strings. And if the lengths are the same, it just uses the normal string comparison, which will be alphabetical. And then here, otherwise, it preferences the longer strings. So it sorts them in the order of length. So let's run this again now. I'll run the boggle program again. It takes a moment. I don't know if you noticed that. It just took a little moment for it to do it. Okay, there's lots of 3-letter words. And then up the top here are some longer words. There you go. We got, so that's some word I don't even know. There's supposedly an English word. So we've got one 7-letter word and a bunch of 6-letter words. All right, for this particular boggle here. All right. So that's great, but let's go and see if we can optimize it. All right. So someone says, remember seeing oven in the words, but okay. So the person's asking this question. Austin's asking a question. Just bear in mind that the test is using this fixed set here of letters, and when I'm actually running the game, I'm actually making a new set each time. Okay, I'm making a new set each time. So that particular one would have had a V in it, presumably. I hope that was the case. All right. So each time we run this, we've got a different boggle. We can make that the same if you want by setting the. In fact, we're going to do that right now. Let's do this. Let's change the shake. Where is it? Where's our shake thing? Okay. Let's put a random seed in here so that now when we do our next step, we keep getting the same boggle each time. Let's have a look at that and we'll get used to it, whatever it is. Okay, so it'll be random, but it'll be the same one each time now. Okay, there it is. Oh, it's got lots of X's and Y's. All right, so that's not a very good one. Let's just put a different seed in. So I hardly found any words. That's terrible. That's because it's got lots of X's and Y's in that particular random boggle. Let's just go for another one. I don't like that one. Okay, this one is more promising. It's got a lot more vowels in it. There we are. Lots of words. Okay. Tons of words. Okay, so that's the set of words. Okay, and each time we run this, we should get that same. Okay, so I found 161 words. We run it again, and it should get the same. Now, my question to you all was, how can we make this faster? What can we do to make our search more efficient? There's 2 things at least we can do to make this more efficient. Anyone know? Let's also time how long it takes to run. Okay. Does it tell us how long it takes to run? We can do that ourselves. Okay. Long start equals system. I don't know if this is not necessarily the way you want to do it at home, but this is the way I do it in the lab for our real experiments. So we'll just do this. Long and equals okay, so what that's going to do is take the time before we solve it and the time afterwards. And then we will divide that by, it's nanoseconds divided by, I wish I should have done milli time. Okay, let's just change it to milli. Current time milli, that'll do. So milliseconds is, I think, plenty enough. There we go. Okay, so now we've got milliseconds in, then I'll say duration. Okay, and we'll run this again and see how long it takes. Okay, so now we've got a little timer, which is timing how long that solution takes. It's taking a while, right? There we go. It took a little while, and see how long it took. It took 2.2, it's just over two seconds, okay? All right, so what have we got here by way of make a smaller dictionary? Aha, how can we make the dictionary smaller? How can we make the dictionary smaller? Check if the current word is a prefix for one of the words in the dictionary, otherwise discard. 2 great suggestions there, let's give it a go. Okay, 2 great ideas. So the question is, how can we make the current dictionary smaller? Okay, can we make the current dictionary smaller legally? Okay, well, legally the way we can do it is we can say, let's exclude any word which can't possibly be made from this boggle, right? So what we can do is we can just say, here's the letters in this boggle, right? Create a set of, so we'll make a function here called boggleable, very Good English word there. We'll make it a function called boggleable. And what we'll do is we'll only include words that can be boggled, right? That actually make sense, okay? So, so we'll do this, and then when we go and read the dictionary in, yeah, for example, we can remove 2 letter words, but we can also remove ones that don't have letters in them that aren't in our 16. We've only got 16 letters, right? Well, maybe even less if it's a set, right? So we can just exclude any word. So imagine that our boggle has no Z in it, right? Which is quite likely. Then we can exclude any word that has any Z anywhere in it, right? Because we can't possibly make that word, all right? So that's what we're going to do, is we're going to prune our dictionary to only include ones that have those. That's not doing a search. We don't even know. And obviously ones with more than 16 letters, we can remove those too. So let's start off with writing this function here called boggleable. And then when we read the words in, we'll check whether the word is boggleable before we add it to our set of words, right? Static void boolean boggleable. I don't know how to spell boggleable. All right. String word, and we'll take as a list all the characters that are usable. Actually, we can. Yeah. Okay. The question is, the usable characters, should they be a list or a set? Right. It needs to be if we want to do this smart, we'll take a list rather than a set, because that allows us to count the right number. So, for example, if we had 2 O's and there was a word in the dictionary with 3 O's, we'd discard it, okay? Because we've only got 2 O's, right? So if we take a list of all the characters that we have, then we can we can deal with that. All right. So let's just try that. So list of character. And these are the usable ones. And then we'll return true or false, depending on whether this particular word can even work. All right. So first of all, if word.length is less than 3, or word.length is greater than 16, then return false. Right. It's not a legal word. Okay. So that's one way to prune it. Okay. Then what we're going to do. Actually, this should be a. What I'm going to do here is say char. Where is our boggle? Yeah, we'll just take the boggle in here. Okay, so let's just do this. So we'll just take in here the actual boggle, right? So that'll be a list of 16, right? List of 16 characters, and then what we'll do is in here we'll create our list of letters. We'll call it usable. And we'll create that from that list that we just got. Equals array list from the boggle. I think that'll work. Oh, we're going to create a new. Right, forgot to write new. There we are. Okay. All right. The problem here is that there is an array of char, and this is expecting characters, so that won't quite work. That's annoying. All right, doesn't matter. We'll just do this. We'll just do it like this. So what we'll do instead, we'll do it. Whoops. There might be a simpler way to do this, but I don't know it off the top of my head. So we're just going to write a simple loop here and put all the letters into our list. Okay. So the reason why we want to put them in the list is because we want to remove them once they're used. We want to remove the letter once it's used, okay? That's why it's important to put it in the list. And if it was a set, that wouldn't be good because you might actually have 2 O's there and you need to know that there's 2 O's. Okay, and a set wouldn't help you with that. Let's try boggle. No, boggle is, I don't think we can do that. Let's try boggle as, no. You can't do that on a char. If it was an array of character, maybe you could. Anyway, all right. So we'll just do for int I equals 0. I is less than boggle.length I plus plus, and then we'll just add each one into the list. Okay, so usable dot add boggle I. So we've just gone and added all the letters in our boggle into this list, okay? Then what we're going to do is we're going to use up the list as we go through the letters in the word, and remove letters from our list as they get consumed by the word. And if we get to a letter and there isn't one in the list, then we know this word can't be made, okay? So that's how we're going to do it. We just say, so for int I equals 0, I is less than the word length, right? I plus plus, then we'll say if usable dot contains the letter, so that's going to be word dot char at, oops, goodness, word dot char at I. Okay, if it contains that, then we want to remove it, right? Then we'll say usable. So that's good. It's all good, but we need to take it out of our usable set now, so it's no longer usable. Dot remove. So we're removing it from the list. The same thing here. I'll just write this a little bit simpler. So that's the letter, is the char out there. So that's the letter. Oops, goodness, another typo. There we are. So now we're going to say if it contains the letter, then good, but we need to remove it. Else, if it doesn't contain the letter that we need, oops, semicolon, if it doesn't contain it, then we're done. So we return false from this function. Else, return false. Okay? So if ever we get up to a character which is not in our set of usable letters, then we return false. But if it is up to our set of usable letters, then we continue, but removing each letter as we go along. And if we get to the end, then our word's good. So now, what we need to do is we only add it if boggleable word we need to pass the boggle. So read words, we need to pass the boggle to read words now. Where is it? Where's read words? Okay, so we need to pass the boggle in here. So where is it? Boggle, yep. So we pass that in there now and change read words to include that check. So char like that, boggle. There it is. Okay, so we've now passed in our boggle, and going to pass it in here when we do our check. Here it is, boggle, like that. Okay, so if the word is boggleable, then we add it to the set of words. Otherwise, we don't add it. So now let's run the thing again, and we're going to look for two things. We're going to look to see how much the oh, someone's found out a shorter way to do this. All right, so what we're going to do is find out how much we prune the dictionary and what that did to the time. So notice that's how long it took to run last time. Now let's run it again. This is not very scientific, by the way, because you need to run it multiple times if you really want it. Okay, it all just crashed and burned. What happened there? All right. Index out of bounds. Index 65 out of bounds for length. Where's that? My goodness, what's happening here? Boggleable. Remove L. Oh. Oh. What's happened here? If it contains it, what have I done wrong here? Okay. Oh, that's right. I need to give the index. Okay, I need to give the index. Remove requires the index. And so what I need to do here is I need to say, find out where L was, which index it was. Okay, so to do that, it's a little bit tricky. So I need to say usable dot index of L. I think like that. So what that'll do is it'll tell us where L is in the usable array, and then say remove the one that's in that position. All right, slightly awkward way of doing it, but that's how we can do it. Like this. Okay, it did it. Now notice that. Okay, so two things to notice here. Let's see what happened at the time. It was 2 seconds before. Same time. All right, it hasn't changed the time at all. It's interesting. But we massively reduced the word set. Okay, massively reduced the word set. Let's run it again. And Okay, so that didn't make a huge difference, but it did reduce the word set. Okay, now the other suggestion that someone made, which is another great one, that says let's create a set of viable prefixes. What that means is that as we create our set of words from the dictionary, we can also create all the prefixes, and we can stop searching if we get to a string. We're building up these strings. If that string, even if it's not a word, we can see if it's the beginnings of a word. If it's not the beginnings of the word, there's no point in keep looking. Okay, can we just stop looking at that point? So if we know what the beginnings of all the words are, then that's useful. So question for you all. Can you guess what the relationship is between the set of all words in our dictionary and the set of valid prefixes in the dictionary? Presumably there's a lot more prefixes than there are words, right? So guess how many prefixes there are. Say we've got 1,227 words there. So how many prefixes do you think they're going to be? We'll start writing the code for the prefixes, okay? So find words, read words, where's read words? So read words, where is it? Okay, prefixes. So I'm going to create a set here of prefixes, which is going to be the beginnings of words. Prefixes. And we'll pass that into here. Like that. And then up here, we're going to pass in, someone says there are only going to be 100 prefixes for 1,000 words. Do you think so? Yeah, but you'd think there'd be a lot more. Each word has multiple prefixes, right? So if I have the word prefix, the prefixes of prefix are P, PR, PRE, PREF, PREFI, PREFIX, PREFIXE. That's all the different prefixes of prefix. Okay. Yeah, it doesn't matter how big the dictionary is, but we can stop sooner. If there's a word that, yeah, that's a good point. But actually pruning the dictionary may not make much difference. That's a good point. But having a smaller set might be helpful if it's giant. Someone raised a very good question there. Okay, so now we've got a set of prefixes. Read words. Sorry, where are we? Read words, prefixes, and boggle. What have I done here? What's going on? Set of string prefixes. Why is that red? What is it saying here? Type parameter boggle. Oh, sorry. I've just mistyped. That should be a comma. All right. So now we're going to create our prefixes. Yep. So we're going to create our prefixes here. So the way we're going to do that is if we get a valid word, only when we get a valid word, we'll also add all the prefixes of that word to the list of prefixes. Okay. So in here, we're going to increase the set and say, okay, here's all our prefixes. Okay, so we're going to say for int I equals 0, I is less than word.length. Word.length. Okay. I plus plus. And then what we're going to do is add it. Okay, so we'll say prefixes dot add. Now it's the substring, so it's going to be word dot substring 0. So from the beginning and to I, and it's not inclusive. So all right, so that should do it. Now. Okay, so that hopefully will do it. I think that's right. So we've gone and created ourselves a set of prefixes. We're not using them yet. Let's see how many there are. Okay. Okay. Let's go up the top here. What did we get? Okay. Interestingly enough, the number of prefixes is about the same as the number of words. And this is actually a result that you'll see time and time again. If you look at the prefixes of a set of words, that set of prefixes is about the same size as a set of words. Some people think the number of prefixes is going to be massively higher. Other people think it's going to be massively lower. It's not. It's about the same. All right, so now we've got a set of prefixes. The question is, what do we want to do with that? So we've got that. So what we can do now is we can just stop searching as soon as we find that the prefix isn't there. Okay, so find words. Okay, if the candidate length is that and the word contains that, then we can continue. Okay, so that's what we had before. But what we're going to do now is if it isn't like that, say if prefixes do this stuff. Oops. Okay, so we need to pass the prefixes, of course. So set of prefixes. So what we're going to do now is we're going to say, look, there's no point in continuing to look if the prefix, if the beginning of this word isn't a valid prefix for any of the words. Okay, so we're going to do this. And then, of course, we've got to pass it again here. Okay, good. All right, so all I did there is pop that in. Okay, so we're not going to continue unless the beginnings of this word that we've got is actually a valid beginning of a word. And then all we need to do here is pass the prefixes in. Okay, now let's see what happens to our time. And hopefully it'll still work. Okay. Okay, that was noticeably faster. I don't know if you saw that on the video, but there you go. All right, so we found the same number of words. We found exactly the same words, so it didn't affect which words we found. But instead of taking 2 seconds, it took 200 milliseconds. Okay, so it took about 1/10 the time. Okay, so there ends the lesson, folks. What we've done is we've created a game from scratch. Let me just quickly go over it for those of you who got lost in all this stuff. We've created a game from scratch. It solves boggle. We've got a little thing up here which tells us where our neighbors are, okay, which gets initialized when the program starts. That's what the static thing is doing. It's initializing this neighbors set at the start. Neighbors is a list of sets, one set for every die, which tells us where that die's neighbors are. Okay, we've got a test for the neighbors to see if this is correct, and we found out that our test wasn't very complete because we found 2 bugs in here. And this didn't find those bugs. Okay, so that's a lesson about bugs. We've got this little code here which we wrote a few weeks ago, a week or so ago, which actually just rolls the dice for us. Okay, and we've got a little thing here which checks whether or not the word that is in the dictionary is actually one that can be boggled. And then we've got this thing here which will read the words in and will only include ones that can be boggled and builds up a set of prefixes as well as a set of words. Okay. And then finally, we've got a fairly simple little function. This is actually the core of the search. It's just this. Okay, so let's just go through it. This is all there is to it, really. Okay, so we start by marking off the die that we're up to. Okay, because we can't reuse it. At the end, we unmark it, saying it can be used for another search later. Okay, and then what we do is we say the string that we've made up is of whatever we were given, which initially is nothing, plus us. Okay, so at the beginning, it's just like the letter H. All right, and then if we're the right length, so we're greater than or equal to 3, and our letter is in the dictionary of valid words, we can get rid of this, by the way, now, because our valid words only includes ones of that size, but it doesn't matter. Then we add it. It means that we actually found a valid word. So if the thing that we've got so far is in the list of valid words, then it means we found it, and then we can add it to our set of boggle words. Okay. Otherwise, well, not otherwise, regardless of that, we continue and we say, if the prefix contains the candidate, prefixes contains the candidate, which will also include this case, then we go through each of our neighbors and try and grow the word longer. Okay, so we try and grow the word longer, and so and if it's okay, so we try and grow the word longer if the prefix is in there, and then what we do is for each of our neighbors, we say if we haven't already been to our neighbor, then we recurse and just find the words for that neighbor, growing the string. Okay, that's it. So it's actually only a few lines of code, the core of this algorithm. Just really this part here is the core of the algorithm, and that is how we solve boggle. And all the other stuff is just all the stuff we do to help us. Any questions about that before I move on? Okay, I think we're good to move on. And it's time, I think, to do some revision. So what questions do you have for me? So questions for the any part of the first 5 weeks of the semester, and particularly questions for, does this algorithm have a specific name? No, it's just one I made up. This sort of algorithm is pretty standard. Okay, so I mean, it probably does have a name. It's just I say I made it up. It's kind of okay. Interleaving arrays. What is the specific question? Katrina asks about interleaving arrays. Specifically, what? Have you got a specific question? If you can tell me specifically, I'm very happy to do that. Particularly if the more concrete the question is, the easier. Let's see. Is it something on the course webpage? Is it in one of our labs or something? All right, I'm going to answer Katrina's question first, but I need to know more info. Then Lewis asks, I'm going to go to Katrina as soon as she gives me more info. Mid-semester practice exam. Okay, what was the question? Let's go here. I hope that I can actually see it from this computer. Sample exam. Hopefully this will work. Yeah, all right. So, it'll be in the repo, won't it? Okay, you got to, where is it? Wait a second. Mid-semester exam. Where is the repo? Here, sample exam, you need this repo. Is this what you're talking about? Okay, I need to log in. Okay, so where is the question? Katrina, which question? Interleave, okay. All right, so let's look at this question. All right, so let's, what I'm gonna do is Q2 interleave. I'm going to try and do this right now. I don't have the, I'm not sufficiently prepared to do the tests and everything, because I don't have the I don't have it set up in IntelliJ to do that, and I can't go and clone the repo and all that sort of stuff right this instant. But what I'll do is I will try and write the code right here, and hopefully we can test it enough just in this environment. Okay, so new Java class 01, so revision 1. Oops. Interleave. Oops. Sorry, folks. Just forgive me here. Q2 interleave. R01.Q2 interleave. Good. All right. So this is a revision lecture. Interleave, and then let's paste all this stuff in here. There it is. Okay. All right. Let's have a look at this question. Good question. This function takes two arrays of strings and returns a new array of strings where the elements from A and B have been interleaved. So if you take A, okay, so that's one array, that's the other array, and the result will be that. Okay, and they're going to be, okay, all right. Right, let's go through this methodically. What's the time? I'll try and do this in less than 5 minutes, okay? I'll spend 5 minutes on this, then I'll move on to another question. So folks, if you see questions there that you would like to upvote, please do so, okay? All right, please make it clear which one you want me to do next, and I'm going to focus on this now. So the first question, Katrina, is to ask the question, how long is the result going to be? Because we probably want to, I don't know, I'm just making this up. It's a long time since I wrote this or have done this, okay? So I'm just making this up as I go along. But the way I would think about it straight away, and by the way, this is not using sets and so forth, I don't think, probably, because this is intended to be for a question that's from early in semester, so you don't necessarily know about sets and all those sort of types. So yeah, so you're going to create an array that's equal to the length of the two arrays. So let's just do that to start with. So string result equals actually if it's just a here's a really simple way to do it, which is not actually, which makes it even simpler. Okay, yeah, you can do that. You can create oh, it is an array of strings. Sorry, yes, you're right. Sorry, for some reason I was thinking they were actually two strings. All right, so yes, we want to create an array of strings that's the right length. Okay, for whatever reason I was thinking they were actually, these A and B were strings. No, they're arrays of strings. So we want to create a new array. So new string array which is equal to the length of a dot length plus b dot length. Okay, like that. All right, so there we go. That's the result. That's going to be something like that. Then what we want to do is to go through the two, starting, and it's got to be a. All right, so what we might do, there's lots of different ways to do this. Let's just start off with basically what you want to do is you want to go through adding A and B until one of them gets exhausted, right? And then you just add the other, okay? So you want a while loop that keeps going until either A is at the end, that both A and B are exhausted, okay? That's going to be the basic thing. So we're going to have a while loop that's going to keep going until A, we'll call them I and J, int I equals 0. That's going to be for A, int J equals 0. Well, let's make it a little bit clearer. Let's call it AP, that's A pointer, and BP, B pointer, okay? Or counter, or B index. Let's just call them I for index, okay? AI and BI, right? And we're going to call them both 0, okay? And then what we're going to do is do a while loop while AI is less than A dot length. Okay, we're going to keep doing this while that's true. Or B is BI. By the way, folks, I'm just making this up. I'm sure some of you are smarter than me and you will have a better solution. So don't take this as the best solution necessarily. When I say sure, I know some of you are much smarter than me and you'll have a better solution. So I'm just making this up. So we're just going to go through this loop as long as one of them isn't, as long as one of them is not exhausted, we're just going to keep going. So at the end, they'll both be exhausted, okay? So then what we're going to do is, and we need to have a counter for RI, int RI equals 0. That's going to be where we're going to put the stuff, okay? So then what we're going to do is we're going to say if AI is not equal to is less than A dot length, as long as there's still stuff for A, then you put in an A1, then you put in a B1, okay? If then you say result brackets RI equals A bracket AI, and then we're going to increment both of these. So we can increment them in place like that. Okay. So that sounds all right. And then, so we don't even need these curly braces. Okay. And then do the same thing for B. Okay. So say if BI is less than B dot length, then result bracket BI plus plus equals B. BI plus plus. Oops, I made a mistake there. I'll come back and fix it. Like that. RI, there should be RI there. Okay, and I think that will work, right? Return result. I think that's done. Let's have a look. Like I say, I'm just making this up, so I could easily have made a mistake here. So let's just quickly work through what I've done. So we're going to go through and you're going to keep doing this loop until both of them are exhausted, okay? Both A and B are exhausted. This loop will just keep going around until they're both exhausted, which is what we want. Now, if A is not exhausted, which is this case, then we're going to put the next element of A into the result. And if B is not exhausted, then we put the next element of B into the result. All right, I think that'll work. The problem is writing a test for it. I don't know. Did that? Is there a test? Is there a test here? I don't know if the tests are visible here. Sorry. Just give me a second. Tests. Oh, cool. All right. Interleave.test. Okay. Let's just see if I can just chuck this whole thing. Let's see if we can test this. Maybe we can. And then we'll move on to the next question. So we'll say file, new Java class, Q2 interleave test. That. Add it to Git, yep. And then we'll just drop this whole thing in here, hopefully. See if this works. All right. And then test, blah, 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 blah. Q2 interleave. Let's just see if it works. I don't know. I haven't kind of see. It may fail because I haven't checked the class names. There you go. It worked. Wow. Amazing. All right. Hopefully that helped, Katrina. Any other questions? What's the next question here? Someone deleted their complaint. Hey, it's okay to make mistakes, folks. It's one of the most important things. You saw me make lots of mistakes with the boggle, all right? If you misunderstood what was going on, that's perfectly all right. What have we got? What's the next question? And someone's got a different approach. That's good too. It's good to look at other approaches, folks. So someone else got a different approach. I'm not going to look at that now because I want to get onto more questions. But please look at other people's approaches. Could you give a brief example of interface teen count? Has anyone got a thumbs up? Oh, use 2 point to index the array. What else has been upvoted? Anything? Okay, upvoted here. Nope. Nothing has been upvoted. Oh, yes, here we go. Yep. Anything else? What is an instance field? What is the difference between it and a class field? This is a really great question. It's really important, okay? Now, there's two parts to that. One is a conceptual question, and the other one is a language question, okay? Because sometimes you use different language. So someone's asking, what is an instance field, and what's the difference between a class, it, and a class field? Now, this is a core question in object orientation. Let me see if I can quickly do an example right here and right now using a bike. I've talked about this a lot in the class. Let's just make one up right now. New Java class, bike. Okay, give me a suggestion of a... Give me a suggestion of a class field and an instance field for the bike, folks. Can anyone suggest one? Suggestions for what fields? What fields have we got there for the bike? Instance fields. Anyone? So, going back to the question for you, Fan. So, first of all, the instance fields are properties of every separate object, whereas class fields are for the whole type. Okay, and right, so someone's already given us an example. Oh, hang on, bike serial number. Yeah, exactly. Okay, so model name, number of wheels. All right, so let's look at these examples that people have already put on there. Okay, so for a class of bike, we might say, okay, for this kind of bike, you might have a particular kind of bike. It might be a Giant brand. The brand name might be Giant or whatever, and that will be a property of the class. That is, everyone who's got the same kind of bike as you will have that. Okay, so let's just make this abstract. We don't really want that. We just want to have something else. We're going to call it can someone tell me a model of a bike? Giant something, Giant XYZ. Okay, just call it, let's imagine that's a kind of bike. Okay, extends bike. Okay, so this is a very specific kind of bike, right? And it's going to have a field which is going to be the number of gears, for example. That's a property of everyone who buys a Giant XYZ. Static int num gears. Okay, and we can have another static field that's a property of every single bike of type Giant XYZ, right? Static, what was it? String name, model name, right? These are examples and number of wheels. Okay, some bikes have more than num wheels. Now, all these things here are actually, those ones there are all things that actually won't even change. So we can make them actually even final as well. Final, like that. Num gears equals, let's say it's got 12, all right? Equals 12. And then num wheels, hopefully it's got 2. Some bikes do have 3 and some have 1. They're called unicycles. and then the model name is going to be, and the reason why I'm writing final here is just because these are things that in real life, they're never going to change. So if you buy a giant XYZ, those things are never going to change. There might be some things in the class that does change, but let me add one that might change, okay? And then model name is going to be giant XYZ, right? That's the model name, okay? And then we can have another one, might be something like static final. I'm making this up, so this is a little bit hard here. Warranty period, maybe. And that might be something that changes, right? It's not final, okay? So it's not final, okay? And we can say, we can write ourselves a method saying public static void set warranty period, like that, and then take an int. Int period, and then we'll say warranty period equals period. Right, so that's like how long the warranty lasts. And the company might decide, oh, these are really good bikes. They don't break very often, so we'll increase it. Okay, so maybe it's something that does change, right? Then there are going to be things that are specific to the particular bike. Okay, so they're all things that every bike, every giant XYZ shares these attributes. I use the word attribute in the English sense of the word, not in a technical sense of the word. And then the other ones, so they're static. They are class fields, so they are declared static, like that. Okay. Then what we can do is we can say each bike has its own value for the following. Okay, and then we can say stuff like, I don't know, you can say int final int serial number. I say final because that never changes, right? So the serial number on your bike never changes, okay? And that will have to be created in the constructor. We'll do that in a minute. But there's other things that may change, like int total kilometers. Right, that's how far you've gone. Okay, so they're fields, and then we need to make ourselves a constructor for this bike. So the constructor is going to be like this: say public, well, it doesn't have to be public, but public giant XYZ, and it will take as an argument. It needs to know the serial number and maybe the total kilometers. Okay, so it'll be int serial number, comma int total kilometers, and then I'll say this dot serial number equals serial number, and now the red line's gone because now it knows every time I make one of these, the serial number is set. Okay, you can't have a final variable for an instance variable unless it gets set in the constructor. Okay, so this dot total kilometers equals total kilometers, like that. All right. So then with that we can make a bike. So going back to the question that you found originally asked. So we have here, these are static fields. They're ones that are shared for every bike. Everyone who owns one of these bikes, say you own one, I own one, we each have one of these bikes. Then they've all got 12 gears, they've all got 2 wheels, and they're all called giant XYZ, and they've all got the same warranty period, which might change, but it's the same anyway, okay? And then for your bike, it's got a particular serial number, and it's got a particular number of total kilometers, okay? So then we can write a main method here, bm, and say, we've got to say what its serial number is. Serial number is going to be something like this, you know. And then the kilometers, maybe it's 0 because you just bought it, like that. The serial number is going to be an int. Okay, so it's not a string. It could have been a string, but I made it an int. All right, there you go. So that's a very big number. Let's make it a little bit. It's a bit smaller. Okay, there we go. It might have been better to make the serial number a string, but that'll do for now. And then what we're going to do here is we'll make mine, and it's got to have a different serial number, right? So maybe mine's the one that came right after yours off the assembly line. And it's also, and it's got 5, I know, I just took it for a ride, okay, just before the lecture. Okay, so now what we're going to do is hopefully, let's just write a couple more methods. Public, big, void, set, total kilometers, int km, and we'll say this dot total km equals km. And then I'm just writing something simple here so that we can say yours dot set total kilometers. Maybe you went for a big ride. Okay, and then mine set total kilometers. Okay, like that. All right, now let's do the obvious thing. Throw this whole thing in. Let's get rid of extends bike here for the sake of putting it into the Java Waterloo visualizer, okay? So I'm just going to make it simpler for the sake of the Java Waterloo visualizer. We're going to get rid of that and drop this into the Waterloo visualizer. And hopefully this will help. I always forget the URL for the Waterloo visualizer, but you can always find it by going to the course webpage. Wherever that is, there we go. And we'll go to one of these units like that, and then we can, it doesn't, oh my goodness, sorry, like that. Those ones don't have the Waterloo visualizer, that one does. Okay, so there's the Waterloo visualizer. Okay, so that takes us to the Waterloo visualizer. That was just my very clumsy way of getting to the Waterloo visualizer. And then we're going to say, how do I edit that? I can't visualize that, and we'll stop this. Sorry, folks. Edit code. There we are. That's what I wanted to do. Oh, we can just edit it. Okay. So now I've just, oops. Okay, that's our code that we just wrote. And now let's try and visualize the execution. And hopefully this will help. Okay, so there's our static fields up there. See that? They're the static fields of this type. Okay, the number of gears, the number of wheels, the model name, and the warranty period, which is 0, which is not very good. And then what we're going to do is make this new bike. Bang, there it is. And it hasn't been initialized yet. Okay, so there. So that's your bike with its serial number and total kilometers. And we'll keep going. And that's my bike, okay, with a different serial number, different total kilometers. The values here, the serial number and total kilometers, they're instance fields. Those ones are static fields. Notice that those ones are not for each bike, whereas these ones are for each bike. That's one bike, that's another bike. That's my bike, it's your bike, that's my bike. They have different serial numbers and they could have different kilometers. They happen to have this, well, they do have different ones, but they could be the same, they could be different, okay? And they could have different serial numbers too. They could have the same serial numbers, but obviously in a real world, you wouldn't have the same serial number on two different bikes. But now, hopefully you can see here, there's two different bikes. There's one bike there, one bike there. The bikes have two instance fields and they have 4 static fields. And those are class fields, okay? And those first ones are fields that can never change. We declare them final. This one here is a field that we could change, and we probably want to change it from 0. 0 is not very friendly. Okay, hopefully that helped you. And I'm going to put this back and make it extend bikes again, just to go along with our running example we've had in class. All right, we've got 20 more minutes. What else would people like? What are the stack and the heap? Okay, good question. That's a great time to ask the question. Right, so the heap is the place where objects, when we create an object, it goes into the heap, okay? And it stays in the heap for how long? It stays until we don't need it anymore. What gets rid of it? The garbage collector gets rid of it, okay? In here, they use the word objects. That there, the way we'd call that is the heap. This is the heap, this stuff over here. In this example, there's only 2 things in the heap. In real world, things often have millions. The heaps often have millions of objects in them. Okay, millions. Here in this very, very, very simple example, we have just 2 things in the heap. That object and that object, okay? We use the word instance is often used as a synonym for object. It means, just like in English, the word instance means one example of. I think that's probably the English definition of the word instance. One example of, or one of, okay? So it means this is one example of a giant XYZ. Okay, so giant XYZ is the type of bike, and we have one example of it there and one example of it there. These two things are objects. Okay, the stack has our local variables in it when our program is running. So you'll see here we've got two local variables in this little tiny program. The two local variables are a variable called yours, which is of type giant XYZ, and mine, which is the type giant XYZ. Okay, and then we're going to call two methods on them. One is we're going to set the kilometers on yours and set the kilometers on mine. I didn't actually do that. I can do that now. There we go. So I just set the kilometers up there, and we can keep going. Oh, actually, if I go backwards, you can see more of the question of the stack. So someone asked about what the stack is. This thing here is the stack. These things, that you can barely see the outline, but there's one there and there's one there. They're what we call frames. Notice this one says main. It means that we're in the main method at line 35. There it is, line 35. When we call the method yours, what happens is the information we pass to yours gets passed by this thing called the stack. Okay, so let's just go back a step. Okay, let's just go forwards now. Right, so we've just called it. We've called set total kilometers. We're at line 29, and we've got two arguments. One is this subtle, in Java, subtle hidden argument, which is the so-called this argument, which is hidden. Notice there's nothing up here called this. It doesn't say this, it just says km. So there's km, and km, sure enough, is 120. So you've got an argument called 120, which is that. But there's an implicit argument here, which is this, and there it is there. And what's this pointing to? Oh, look, it's pointing to your bike. Notice that we called the method on yours. What that means is we're actually essentially calling this method with a reference to yours. But the way we write it in Java is yours.setMethod. Okay, and so what that means is do the set method function, this one here, which is an instance function because it doesn't have static at the front. Do that set method function and do it with respect to yours. So it does, and the way it knows which one to do it, which object to act on, is because of this hidden this variable here. Okay, and this variable refers to yours, your bike. Okay, and if we keep running it again, next time we do it on mine. So here it is, mine. Okay, so this time the this variable should point to mine, and the km variable should point to, it should be 40. Okay, sure enough, the km is 40, and the this points to my object. Okay, so we've got two objects in our heap. We've got a stack over here. We've got a main method here. At this moment, we're inside of another method, which what we say it pushes a frame on the stack. You don't, in this class here, we don't actually teach this stuff. There are other classes that do teach this, but nonetheless, this is what we call a stack, and it's called an activation stack, and this has one entry for each nesting of methods. And if you have a recursive method, like we used in the boggle example just a few minutes ago, this could get quite deep. Okay? Incidentally, how deep could it get in the boggle? Does anyone know? If we did it right, like in our example, it could get 16 deep, because we could go as far as 16 steps. All right. Next question. Anyone got another question for me? We take the MSE like the lab test. Yeah, the mechanics of the lab test will be just like the, the mechanics of the MSE will be just like the lab test. I explained it at the start of this lecture, okay? I said a fair bit about it at the start of the lecture. It's also on the course webpage. But basically there's a URL. There's a URL which is on the Piazza post. You go to the Piazza, there's a pinned post for week 6. Go there, it tells you a bunch of stuff, points you to the course webpage. There's a URL there. You go to that URL, you won't be able to access it until the exam starts. As soon as the exam starts, you'll be able to access that URL, and then you better clone that thing. You'll be able to work on it inside of IntelliJ, and then when you finish questions, push them, okay? And you only get marked on whatever gets pushed. If you don't push stuff, it doesn't get marked, okay? And as soon as the exam's finished, you can't access the server. Okay, that's how the technology works. It just cuts off access to the server. On lecture notes, the type of an instance determine the method. What does that mean? Leo's collated them in a message further up. Okay, from Leo. What do inheritance and interface do? Okay. Okay, great. Okay. What do inheritance and interface do? So inheritance, these are two different but related ideas. The best way to look at, oops, I just lost power. Oh my God. Can you still see me there, folks? Hopefully. That was cool. I just accidentally kicked the power switch, literally. All right, we're back. Great. So inheritance and interface. If you go to the there's a lecture where I go this in great detail. One of the O lectures where we do all the different animals. Let's have a quick look. Where is that? Can anyone remember which one that is? Let's have a look here. One of these ones. Not O2. Must be, maybe it's O3. No, it's an O4. Okay, so here, what do inheritance and interface do? So here you see a whole lot of classes, okay, and one interface. That's an interface there. It's called Venomous, and you can see in IntelliJ gives it a different icon. It's got an eye and it's green. These ones here are all classes, and they're blue. To answer your question about what inheritance and interface do, I highly recommend you go and look at the lecture for 004. And how do you do that? Let's just quickly go back and show you how to do that, because you really need to know how to do this. It's really worth doing, and everyone should know how to do this. Okay, so you go here, and you go to 00, object orientation, you go to 004, and you click play. And that will tell you all about inheritance and interfaces. It gives you a very good, I hope, a very good example. And you'll see that there's inheritance, because in this particular example, you've got a hierarchy of creatures, starting with animal. And we notice that you can't actually make an animal. Animal is, wait, let's go to 5. In 5, we make it slightly better. Okay, we refine this further in 5. Most of the ideas are in 4, but we make this even more refined in 5, where we go to animal and we say this is abstract, because you can't make an instance of an animal. Okay, you've got to be specific about which animal you want. You can make an instance of a dog, but you can't make an instance of an animal, because an animal is really an idea, a concept, not a concrete thing. Okay, so you can make an instance of a dog, but you can't make an instance of an animal. And in Java, we say that by saying this is abstract. It's an abstract idea. Okay, and then what we have is we have a mammal. Where is it? Here's a mammal, which extends animal. Okay, and then we've got where is it? Dog, which extends mammal. Okay, so you have a relationship. In the top, we always have Java lang objects. So we've got Java lang object, then we've got animal, then we've got mammal, and then we've got dog. Okay, so that's an inheritance hierarchy, and that mirrors what we see in biology or whatever. There's very many things in the world that have this sort of hierarchical relationship of ideas. Then there are some other ideas which are completely distinct from this notion of inheritance, and in the example we give here is venomous. Okay, so the idea of whether something is venomous or not is actually quite separate to where it fits in this hierarchy. Okay, so for example, you can have a platypus is actually venomous. It's got a venomous spur at the back there, so it implements venomous. And also, obviously, a brown snake is venomous, and also there's a spider in here somewhere. Yeah, redback spider is venomous. They're all venomous, okay? And but they have no relationship to each other in the family, in the tree of animals, okay? They're in very different places in that tree, but they all share the property that they're venomous. Okay, so the property of being venomous is a separate idea to the notion of the relationship between the animals. It's just something they have in common. And the example I've given many times in the lectures is the idea of something like transport. And you can say this thing is transport, even though that one there is an animal, like a horse or an elephant, transport. Whereas this thing over here, train, is also transport, but it's a machine. Okay, so machines and animals don't have much in common, but they could both be transport. All right, will array list be tested? The answer to that is very clear on, I don't have that answer in my head, but the answer is very clear on the course webpage, where it tells you up to where the exam is. I think it's the end of week 4 if I'm not mistaken, but that's very clear on the course webpage. Go to the description on the course webpage of the exam. It says exactly where it's up to. Okay. What if the clone process is very slow during the exam? If the clone process is very slow in the exam, I'm afraid there is absolutely nothing I can do about it. Okay, it's a very good question, but there's nothing I can do about it. So if your computer's really slow, or your network's really slow, or you kick the power like I did a short while ago, I'm afraid there's absolutely nothing I can do. That all we can do is say, okay, the exam's redeemable. All right, so that's really unfortunate. This is one of the ugly consequences of COVID. Not just me kicking PowerPoints in my tiny little office, but also the problem that you don't necessarily have good connectivity from your house. Unfortunately, that's something that's outside of my control, and you're just going to have to run with it, I'm afraid. If this happens in the final exam, then you'll have to lodge an ANU application for special consideration and explain what happened, okay? And ANU's got processes for that. So we try to treat everyone really fairly, but there's absolutely nothing I can do if your internet connection is slow. There's just nothing I can do about that, I'm afraid. So you just have to hope that it's not slow, all right? Obviously, if I did something wrong, or the university did something wrong, like all the university servers died or something, then we'd have to scratch the exam or something like that. And it's not inconceivable that would happen because they've never run an exam this big before, or not with a CI. So that if that were to happen and it was the university's fault, then of course we'd do something. But I can't deal with every separate person's laptops and internet connections. That's outside of my control. Okay. Any more questions? We've got a few more minutes to go. If the server's overloaded, then that's my bad. We'll have to work out how to deal with that if it happens, but it shouldn't be the case. Yeah, what else have we got here? Is there any more questions? I went through the ones. Leo, is there more? No? Okay, last chance to ask another question. Handy IntelliJ shortcuts. Yeah, good question. There are shortcuts in IntelliJ, but listen, some people ask their tutors about fast typing in the exam. I think you're going to find that the exam, most of you won't have enough time to finish the exam. I've said that lots of times. Don't be alarmed by that. That's completely normal. But what will be holding you up is your ability to think through the problem, I think. Okay, so the early questions are really quite simple. They get more difficult. If you're finding you're typing a real lot, then probably you've got the wrong approach to the answer. Okay, I've actually, of course, I've written all the questions. I've also written solutions to all the questions, and I've written all the tests. So I know how to write solutions to all the questions in the exam. There's a lot of them, let me tell you. There's a lot of them, and they don't take very much code to answer each of these questions. So if you're writing a lot of code, that's probably the wrong approach. Okay. So you will be under time pressure, but it won't be about how fast you can type. It'll be about how fast you can think through the problem and debug what you've written. Okay, so IntelliJ shortcuts, yeah, will help as long as you don't fumble the keyboard like I often do, and it actually gives you the code you didn't want. What else we got here? Any other questions? Where will the exam URL be? It's already there. It's on the Piazza post. Okay, I posted to Piazza last night. I posted to Piazza last night a week 6 summary, and in that I gave you the URL. It's there, but I'll announce it on Teams. I also pointed out that on Teams we've got a new channel there called Exams, and in that channel, in there, I'll be announcing the URL in case you missed the Piazza post. How will marks be distributed across the questions? Very, very straightforward. 1 mark per test. Okay, so you get 4 questions. Each question has 5 tests. You get 1 mark for each test. As simple as that. It's as simple as that. What else he did with the boggle game? What's that? All right. Any other questions? Any other questions? If not, we will move on and do our bio. Okay. Of course, I keep saying they're all titans of computer science. They are. We go through great figures in computer science. You all shouldn't be familiar with a lot of these names. There will be the opportunity to be examined on these. Hopefully you'll be examined on them, not in the mid-semester exam, but in the final exam. I normally do. I normally examine you on all these things. Not worth very many marks, but it's important background knowledge. So John McCarthy is one of the titans of computer science, as I've said. There will be no partial marks, by the way. Someone's asking, will the questions be week 1 for question 1? It's not as simple as that, but basically week 1's the simplest question. Week 2's a little bit more complicated and so forth. So John McCarthy, let me get on with this bio. John McCarthy, he's perhaps most famous for being one of the pioneers of AI, for actually making it work. He was at MIT and Stanford, and he's credited with coining the term artificial intelligence. Okay. What's interesting about him, I guess, well, there's many interesting things about him, but one of the things is that he did a lot of development of programming languages and computer architecture and other ideas to help his big goal of AI. So he had this strong belief that in the future of AI, and at the time he died, AI was at a low point, and a lot of people thought, well, that was just a bad idea. Since then, as you all know, AI has become the hottest thing. So it may be hard for you guys to imagine it, but 10 years ago, AI, or maybe 15 years ago, AI was in a bit of a pit. And a lot of people thought, well, that was cool and trendy for a while, but it never really went anywhere. And McCarthy was one of the people who really set it up. So he helped develop programming languages which were going to help them build AI. Lisp is perhaps the most well-known of them, the most closely connected to AI. And it's still a very important language today, and many languages are derived from it. Okay, so Lisp is a very important language that came out of McCarthy's work with AI, and me, of course, as a garbage collection expert, always like to point out that McCarthy wrote the first paper on garbage collection. So he's often credited with inventing garbage collection. He published a paper in 1960. Which described how to do garbage collection. If you go and read that paper, you probably won't understand it. I can barely understand it because the language he uses is not the language we use today. It's kind of weird, but that's all very important. He won the Turing Award in '71, and he had many great students who went on and did amazing things, including another person who we're going to come across later, who is Robin Milner, who's one of my most favorite people in amongst these bios. And Robin Milner wasn't actually the student of John McCarthy, but he did a postdoc in John McCarthy's lab. So with that, we can finish up. We've got 3 minutes to go. Any final questions on the mid-semester exam or on John McCarthy? Okay, if there are not, good luck with the exam. I will be on Teams about 6:15. Okay, 15 minutes before the exam, I'll be on Teams. You should be all ready to go. At 6:30, I'll pull a switch, which will make the server be available to everyone. At that point, you can hit the clone button, and you can clone your repo. Hopefully, it won't take more than a minute for it to be cloned. And as soon as it's cloned, you can start solving the problems. Like I say, the first part should not be too hard, and the last part will be a struggle for most of you to get through. Even for the fastest of you, you'll probably find it tough to get right through to the end. Okay, but that's by design. All right, with that, I will finish up. Have a great week and look forward to Friday. Friday is going to be great with our guest lecture. And please start thinking about questions you might want to ask Amanda. Okay? All right, catch you later.